Morning everyone. So today we are going to talk about an LCR circuit which is equivalent to your damped mechanical oscillator. So let's say you have an inductor, a resistor and then a capacitor. And then there is a battery here. Let's say at this point you have a switch. Let's say the value of inductor is L. This resistance here, we are assuming that this resistance presents or represents every possible resistance in the circuit. आपके सर्किट में वायर की वजह से या किसी भी दूसरी वजह से या एक्चुअल रेजिस्टेंसेस हैं, ये वाला जो रेजिस्टेंस है ये उन सब रेजिस्टेंसेस को रिप्रेजेंट करता है. And let's see the value of capacitor is C. Initially ये वाला जो स्विच है आपने इसको इस पॉइंट पे कनेक्ट किया एंड ये आपका अभी डिस्कनेक्टेड है फ्रॉम हियर. इनिशियली आपने स्विच को यहाँ पे कनेक्ट किया ताकि आपका कैपेसिटर है वो फुली चार्ज हो गया. एंड लेट्स से द चार्ज ऑन द कैपेसिटर इज Q. नाउ व्हेन योर कैपेसिटर इज फुली चार्ज देन एट टाइम t is equal to 0 आपने ये स्विच जो है इनिशियली जो यहाँ पे कनेक्ट किया था अब आपने स्विच को यहाँ से हटा के यहाँ पे कनेक्ट कर दिया है सो दैट आपका जो सर्किट है अब वो ये वाला पोर्शन होगा. दिस विल बी योर सर्किट नाउ. An LCR circuit. Right? Now, in this circuit, there are going to be potentials across inductor, across resistor, and across capacitor. And let's see, across this capacitor, we had plus sign here and minus sign here. Across the inductor, there will be an induced EMF, and you know that across the inductor, the value of the induced EMF is equal to L di by dt. So this will be your induced EMF across the inductor. Similarly, if you talk about the potential drop across the resistor, your potential difference is going to be IR. And the potential difference across this capacitor is going to be Q over C. According to Kirchhoff's second law, which is basically based on voltages, the sum of all the potentials across all the elements in the circuit should be equal to 0. Now, if you apply that, then you will say that you Q over C, which is your potential across the capacitor, plus across the inductor, plus across the resistor is equal to 0. This is what it is going to be because your sum of all the potentials in the circuit should be equal to 0. Now I can slightly rewrite this equation. I can say that your I is equal to dq over dt. Plug in the value of I here. You will say that L, I'm writing this term as first term for obvious reasons because I want it to be a second order differential equation, plus R, this I can again write as dq over dt, plus Q over C is equal to 0. I can still rearrange the terms a bit more and I can write it in this form also. This is a second order differential equation in charge. Right? हम लोगों ने अनडैम्प्ड मैकेनिकल ऑसिलेटर की बात की, फिर हमने उसका इलेक्ट्रिकली अनडैम्प्ड ऑसिलेटर की बात की जो कि आपका एक एलसी सर्किट होगा. and in that LC circuit हम लोगों ने assume किया that there were no resistances present there. Then we started to talk about more realistic cases. We moved to the damped mechanical oscillator where we said that, okay, there are some kind of resistive or dissipative forces present in the circuit. Now, coming to the electrical equivalent of your damped mechanical oscillator is your LCR circuit. So, if you remember your mechanical oscillator damped mechanical oscillator equation, that equation was d2x over dt2 plus b over m dx over dt plus k over m into x. इस इक्वेशन में हमने कहा था x का जो आपका एक जेन्युइन गैस आपका जो फर्स्ट होगा दैट वुड बी कि आपका x शुड बी सम काइंड ऑफ एक्सपोनेंशियल फंक्शन एंड देन वी डिड कम टू थ्री डिफरेंट काइंड ऑफ डैम्प्ड केसेस. In the case of LCR circuit, what we are going to do is that we will draw some kind of equivalence between the terms between your this damped mechanical oscillator and your LCR circuit. And then from there, without doing any derivation, because we have already done the derivation for damped mechanical oscillator. So just by setting some kind of equivalence between the terms, we'll come to the conclusion of underdamped, overdamped, and critically damped LCR circuit. Now, from looking at these equations, there are certain terms which you can obviously conclude from here. You can say that your Q is equivalent to X here. यहाँ पे आपकी सेकेंड ऑर्डर डिफरेंशियल इक्वेशन x में है, यहाँ पे आपकी सेकेंड ऑर्डर डिफरेंशियल इक्वेशन q में है. So q is going to behave the same way as your x was going to behave in damped mechanical oscillator, right? b आपका जो होगा, which was your damping coefficient, that is equivalent to r, the resistance in LCR circuit, and that makes sense also, right? आपका जो damping force होगा उसके अगर आप equivalent कुछ कंक्लूड करना चाहो LCR सर्किट में तो वो आपका रेजिस्टेंस होगा. आपका जो M होगा, M के इक्विवेलेंट वुड बी योर L. नाउ K और M वुड बी इक्विवेलेंट टू 1 upon LC. We already said your M is equivalent to L. That means your K is equivalent to 1 over C in this case. So let me write these terms over here. We are saying that your x is equivalent to q, and which by default means that your velocity is going to be equivalent to I here, right? We said that now your damping coefficient is going to be equal to R here. Your L is equivalent to M here.
मैम
हाँ जी बच्चे,
मैम एक बार ये स्लाइड देखना है, थोड़ा सा कॉपी करना है इसमें से,
इस वाली स्लाइड में से.
हाँ मैम
ओके.
हमें लेक्चर है ना अप्लाइड फिजिक्स.
हाँ जी बच्चे. आयुष गोयल बताइए, इन द मीनवाइल आपका क्या डाउट है?
मैम जी आपने सर्किट बनाया है, स्टार्टिंग में पहले हमने इसको क्लोज किया था, फिर ओपन किया, फिर क्लोज किया.
राइट. पहले हमने कैपेसिटर को चार्ज किया. यू कैन आल्सो अज्यूम दैट दिस बैटरी इज नॉट देयर एट ऑल, एंड यू कैन से दैट एट टाइम t is equal to 0 आपका कैपेसिटर ऑलरेडी फुल्ली चार्ज था. आप ये भी अज्यूम कर.
ओके. और मैम जो हम ये कह रहे हैं कि जो B है यहाँ पे इज इक्वल टू R, मतलब डिसिपेटिव फोर्सेस जो है वो रेजिस्टेंस के यहाँ इक्वल होंगी, मतलब एक तरह से.
हाँ जी.
ओके
मैम जो ये डैम्प्ड मैकेनिकल ऑस्किलेटर के नीचे लिखा है.
हाँ जी, ये इक्वेशन.
यस मैम, ये बता दें थोड़ा सा.
बच्ची आपकी प्रीवियस क्लास में डिराइव की थी. आप थे नहीं, आपकी फर्स्ट क्लास है बच्चे ये.
यस मैम.
व्हाई डोंट यू डू, आप में से जो भी बच्चे जिनकी फर्स्ट क्लास है, आप लोग ये जो पीपीटी है और ये जो आपके क्लास के लेक्चर्स हैं, ये सारे एलएमएस पे अपलोडेड हैं. पीछे के 5 या 6 जितने भी आपके क्लास के लेक्चर्स हुए हैं, वो सारे के सारे उनका जो वीडियो है वो एलएमएस पे अपलोडेड है. यू वॉच दोज वीडियोस. फिर अगर आपको कोई परेशानी होती है, देन वी कैन टॉक 1-on-1, राइट? आपके ग्रुप रिप्रेजेंटेटिव के पास मेरा नंबर है, एंड देन वी कैन डू a Zoom or through phone or WhatsApp, whatever is convenient, right?
Yes.
Okay, please go back to that. For the time being for this lecture, just trust us when we are saying that for damped mechanical oscillator, ये आपकी equation है. B है वो आपका damping coefficient है, जो बेसिकली मेजर है कि आपका जो मीडियम, अलग अलग मीडियम होंगे वो अलग अलग रिप्रेजेंटिव अलग अलग डिसिपेटिव फोर्सेस एक्सर्ट करेंगे, राइट? कुछ मीडियम ऐसे होंगे जो कम विस्कस हैं. फॉर एग्जांपल अगर आपने लिक्विड लिया है, कुछ लिक्विड कम विस्कस होंगे, उनका जो रेजिस्टिव फोर्स होगा वो कम होगा, कुछ जो है वो ज्यादा डेंस होंगे. तो ये जो बी है ये उसका एक मेजर है. जो आपके ज्यादा डेंस होंगे या ज्यादा जो डिसिपेटिव फोर्सेस अप्लाई करेंगे उनका बी उतना ही लार्ज होगा. सो एंड देन एम इज द मास जो आपने स्प्रिंग से अटैच किया था, के आपका स्प्रिंग कांस्टेंट है. सो फॉर द टाइम बीइंग just trust us when we are saying कि ये आपकी damped mechanical oscillator है, and then go back to the videos there. Okay, so we said that L is equal to M, and then we are saying that I should have written M on this side because we are writing everything in mechanical oscillator here. We are saying that K over M is equivalent to 1 over LC, which basically means that your K is equivalent to 1 over LC, 1 over C, sorry, right? Because L is equivalent to mass. So based on these equivalences here, when we solved our damped mechanical oscillator में we said कि आपका जो solution होगा, that would be of this type. A e raised to power minus b upon 2m t cosine of omega t plus phi. And remember, this omega is different than, this omega is not equal to square root k over m. This omega was equivalent to your omega naught square, which is k over m, minus b upon 2m whole square. And this solution was only in the case of underdamped oscillator. We said there could be 3 possible scenarios in the case of mechanical damped oscillator. हमने कहा there can be an overdamped case. Overdamped में हमने कहा कि your b upon 2m has to be greater than omega naught, right? That was our condition for overdamped. यहाँ पे आप इन सब टर्म के इक्विवेलेंट टर्म प्लेस कर दीजिए. b is equivalent to r, m is equivalent to l is greater than omega naught, and omega naught is your frequency of LC circuit, ideal LC circuit जिसमें कोई resistance नहीं है. So your omega naught here is equal to 1 upon square root of LC, right? This would be your overdamped case. And similar to mechanical oscillator, overdamped may be conclude that these are actually not oscillatory motion. इसमें क्या होगा, आपका जो equation का solution आएगा, and here equation का solution means how your charge is going to change as a function of time. वो simply exponentially decay कर जाएगा. Second case जो हमने discuss किया था mechanical में, that was critically damped. Critically damped में हमने कहा था your b upon 2m is equal to omega naught. Here that means your r upon 2l is equal to 1 upon square root of LC. In this case, ये जो आपकी particular value of resistance है, इसको बड़ी बार critical resistance भी बोलते हैं. And from here I can calculate the value of critical resistance. आपके जो critical resistance की value आएगी, that would be 2 times L by square root of LC, which basically would be your equivalent to this. सो अगर आपको कोई LCR सर्किट दिया है जहां पे आपको इंडक्टर और कैपेसिटर की वैल्यू दी गई है एंड आपसे पूछा जाता है कि व्हाट कुड बी द वैल्यू ऑफ रेजिस्टेंस सो दैट दिस सर्किट इज अ क्रिटिकली डैम्प्ड सर्किट, तो आप वो वैल्यू यहाँ से कैलकुलेट कर सकते हो। अगर आप इस वाले केस में बात करते हैं कि आपका जो ये है क्रिटिकली डैम्प्ड सिस्टम में चार्ज जो है वो फिर से एक्सपोनेंशियली डिके करेगा एंड इसका जो एक्सपोनेंशियल डिके होगा दैट वुड बी फास्टर देन ओवरडैम्प्ड, similar to your mechanical oscillator circuit. So this will correspond to your case 2 and this was your case 1, overdamped. Now talking about the third scenario, which is your underdamped. Again, like in the case of mechanical oscillator, LCR circuit may be, if your circuit is overdamped or critically damped, आपका चार्ज जो है वो oscillate नहीं करता है, आपका चार्ज it's going to simply decay exponentially. The third case is underdamped, जिसमें actual में oscillations होते हैं. Mechanical oscillator में underdamped में हमने condition की थी that this should be less than equal to omega naught. Similarly here also then you can say that in the case of underdamped your R upon 12 should be less than 1 upon this value over here. अगर आप underdamped का चार्ज का प्लॉट करते हैं एज अ फंक्शन ऑफ टाइम, सो एट टाइम t is equal to 0 आपका कैपेसिटर फुली चार्ज था, सो यू विल स्टार्ट फ्रॉम समवेयर हियर एंड आपका जो चार्ज है वो ऑसिलेट करेगा समथिंग लाइक दिस विद डिक्रीजिंग एम्पलीट्यूड. कितना ये एम्पलीट्यूड डिक्रीज करेगा, ये वाला जो एनवलप है, दिस यू कैन डिसाइड बाय दिस फैक्टर हियर. जो आपने मैकेनिकल में कहा था आपका चार्ज, आपकी जो पोजीशन है एज अ फंक्शन ऑफ टाइम, इस एक्सप्रेशन में लिख सकते हो. सिमिलरली इन एन LCR सर्किट फॉर एन अंडरडैम्प्ड केस यू कैन से दैट आपका जो चार्ज एज अ फंक्शन ऑफ टाइम अगर आप लिखोगे दैट वुड बी इक्वल टू Q max. Remember A was your amplitude, e raised to power, your B is equivalent to R upon 2L T cosine of omega t plus 5. ये जो आपका एनवलप है, दिस एनवलप दैट वी आर टॉकिंग अबाउट, कि ये एक्सपोनेंशियली कितना फास्टली फॉल करेगा, दैट इज डिसाइडेड बाय e raised to power minus R upon 2L into T. Q max corresponds to your charge if there were no resistances present in the circuit. Now since resistances are present in the circuit, so आपका जो amplitude है which is given by this term here, this is going to be an exponentially decaying function. Over the time आपका कैपेसिटर पे जो चार्ज accumulate होगा वो reduce होता जाएगा and eventually your charge is going to die out and you will see an oscillatory pattern here, something like this.
हम इसमें फेज डिफरेंस कैसे कैलकुलेट करेंगे?
हाँ जी,
इसमें फेज डिफरेंस कैसे कैलकुलेट करेंगे?
this 5,
यस मैम.
you mean to say put time t is equal to 0.
ओके.
At time t is equal to 0, we said your capacitor was fully charged.
हम्म.
So your this
yeah,
side becomes equal to Q max, right?
yes.
We
So
said your QT is equal to Q max e raised to power minus R upon 2LT cosine of omega t plus 5. At time t is equal to 0, you said your capacitor was fully charged. So Q is equal to Q max. Q max is equal to Q max. यहाँ पे t को आप 0 पुट करोगे तो 1 हो जाएगा and this would be equal to cos of phi, which basically means that your cos phi is equal to 1 and phi is equal to 0 in this particular case. So that's how you can calculate the value of phi.
okay.
Now
Ma'am?
talking, हाँ जी बच्चे,
ये जो Q max है वो C times V ही होगा ना?
Q max will be equal to C times V. हाँ जी बच्चे.
ओके मैम.
And then because your voltage is now going to be a function of time, right? So Qmax would be equal to your initial potential across the capacitor. क्योंकि आपकी एनर्जी डिसिपेट हो रही है ना बच्चे इस सर्किट में, राइट? इस वाले सर्किट में अगर आप बात करो तो आपका ऐसा नहीं कैपेसिटर हर बार आपका Qmax पे चार्ज होगा, राइट?
यस मैम।
ओवर द टाइम आपका चार्ज जो है वो रिड्यूस होता चला जाएगा।
हाँ, लेकिन जो Qmax है वो चार्ज की मैक्सिमम वैल्यू है, इसलिए इनिशियल वोल्टेज लेना है ना।
हाँ जी, हाँ जी। So this should be equal to your initial voltage.
ओके।
Okay. Now talking about this omega here, this frequency, right? We said this is not frequency of your LC circuit. Remember in the case of damped mechanical oscillator, we said that your omega is equal to square root of omega naught square minus V upon 2m square. That means in your damped electrical circuit, which is basically your LCR circuit, your omega now would be equal to omega naught square, which is your 1 upon LC minus R upon 2L whole square. And let me repeat that, even though this omega is less than your undamped frequency, right? आप undamped frequency में से कुछ subtract करके उसका square root ले रहे हो. So then this omega is always going to be less than undamped frequency. But this omega is still a constant number. It does not depend on time. So which basically means that in the case of underdamped oscillator, when we said that आपका जो charge है, sorry about the poor drawing, exponentially जो decay करेगा, but अभी भी between any 2 points here, from here to here, आपका जो time period है, वो same time period है जो यहाँ से यहाँ के लिए होगा. It does not depend on time. इसका time से कोई लेना देना नहीं है. Which basically means that अगर आप अपना time period measure करें, so even though your amplitude is decreasing continuously, यहाँ पे आपका जो charge है, amplitude here stands for your charge here. So even though your charge is continuously decreasing here, but आपकी जो cycle का time period है, that is still a constant. It's not as if कि आपके dissipative forces act कर रहे हैं, तो with number of oscillations आपका time period या आपकी frequency कुछ भी change हो जाए. That's not the case here. So this is your LCR circuit. You know what would be the frequency of this circuit. You know how the charge is going to behave. If you know how the charge is going to behave, you can calculate how the current is going to behave in this case, right? Now let's talk about some other terms which we usually associate with these damped oscillations. We'll talk about two such terms. One such term is your logarithmic decrement and the second is quality factor. We'll talk about the physical significance of these terms also.
मैम।
हाँ जी बच्चे, बताइए।
हेलो।
हाँ जी बताइए।
हाँ जी मैम, ये जो हमारी LCR सर्किट में रेजोनेटिंग फ्रीक्वेंसी होती है, रेजोनेटिंग एंगुलर फ्रीक्वेंसी,
हाँ जी,
वो ओमेगा इज इक्वल्स टू 1 अपॉन अंडर द रूट ऑफ LC होती है.
यस, इन LC सर्किट.
हाँ, तो वो ये ओमेगा है या ओमेगा नॉट है?
This is not omega naught. If you write it in terms of omega naught, you will write it omega naught square minus R upon 2L square. Now we are saying that omega naught represents your frequency of undamped case, which basically means that your ideal LC circuit, जिसमें कोई resistances नहीं present होंगे. So this omega is different than that omega.
Okay.
We are going to talk about a couple of terms. Let's start with logarithmic decrement. We'll do the derivation for mechanical oscillator and then because we already established equivalence between mechanical and electrical damped case. So wahan se you can easily replace the terms and get the expression for electrically damped oscillator also. In this case, we said that if this is your x and this is your time, आपका जो है x will go something like this. And we said that you can write x as a function of time in this expression, जो हमारा solution आया था equation का. Again, I can't stress enough that this omega corresponds to your damped frequency. Now, let's take about the 2 points. Let's say this is your point A and this is your point B. At this point, your time period was TA and at this point, your time is TB. इस TA के correspondingly आपका X is XA and this TB के correspondingly your X is equal to XB. Now, the time difference between TA and TB. Can you tell me what would be the relationship between TA and TB? TA में अगर आप एक complete cycle add कर देते हैं, then you get TB. Right? That would be your relationship between TA and TB. Remember, यहाँ पे आप हो and then you are here, exactly at the peak. So you have completed one cycle, and that is why if I add T in TA, I'll get TB, the time corresponding to point B here. Now, from this expression here, if I want to write XA as a function of time, now your time is equal to TA. This would be equal to A e raised to power minus B upon 2m TA cosine of omega times TA plus 5. Similarly, अगर आप point B की बात करते हैं, you can write the similar expression for point B also. Let's simplify this term here itself before going to next step. I can further write this as A e raised to power minus B upon 2m TB cosine of, I'll write TB equal to TA plus T, but I first want to get rid of the extra terms in this expression for cosine here. Omega times TB, I can write TA plus T. And then I'll have phi here, right? Omega is equal to 2 pi by T, right? A e raised to power minus B upon 2m TB cosine of 2 pi by T multiplied by TA plus T plus phi. I can write it in this way also. Now, I can further write it as A e raised to power minus B upon 2m TB cosine of 2 pi by T multiplied by TA. I'm going to move it back to omega times TA plus 2 pi by T multiplied by T. T will cancel each other out. You will have F2 pi here plus phi. I can rearrange it further. Cosine of 2 pi plus omega T plus phi in this form also. If you have cos 2 pi plus x, it's omega TA here, right? We had a TA here. If you have cos 2 pi plus x, that is equal to cos of x. which basically means that I can rewrite this term as a e raised to power minus b upon 2m. And now let's plug in the value of TB here also, which was equal to TA plus T. I didn't plug in the value earlier because otherwise I had to write it everywhere. So you'll have cos of omega times TA plus phi. Now, if I take ratio of both of these terms, XA over XB, and both of these are functions of time. Now, I'm going to stop writing that. So this ratio is equal to A e raised to power minus b upon 2m TA cosine of omega TA plus phi divided by xb. Plug in the value of xb from here. This would be equal to a e raised to power minus b upon 2m TA plus t cosine of omega times TA plus phi. A will cancel, cosine term will also cancel. And from this expression also, your minus b upon 2m TA will cancel, and you will be left with something which would be e raised to power 1 upon e raised to power minus b upon 2m t. And I can take that in the numerator in this way, right? Now, if I take natural logarithm on both sides, your this term is equal to b upon 2m t. And this is called as your logarithmic decrement. And this is denoted by delta. Now, if you look at this expression over here, your logarithmic decrement between these two amplitudes is a constant because your b is constant, it's a damping coefficient, mass of the object is constant, your time period is also constant. So that means if you take any two consecutive amplitude and unki ratio leke, if you take natural logarithm of that, that is always going to stay constant. It doesn't matter आपने first, second का लिया है या आपने 10th और 11th का लिया है. Again, from here you can conclude that if you take any two consecutive cycle and उनकी रेशियो लेके आप उसका नेचुरल लोगरिथम ले लेते हो, that is a constant number. What is the application of this number here? What is application of logarithmic decrement? For example, आपको कोई unknown liquid दे दिया जिसका आपको damping coefficient नहीं पता है. What you can do is that, मानो आपने pendulum ले लिया, pendulum के एक साइड जहां से आप स्टार्ट करते हो, from that point, after one cycle, आपका pendulum जब आता है उसी डायरेक्शन में, you can again measure the amplitude. Let's say आपने यहाँ पे measure कर लिया, यहाँ पे measure कर लिया, आपको ये दोनों नंबर पता है. What is the value of XA? आपको XB की वैल्यू पता है, आपको टाइम का भी पता चल गया है. How much time you require to complete one oscillation. Plug in everything here and you can calculate the value of damping coefficient from here. आपको कोई भी फ्लूइड दिया गया हो, उसका आप B जो है वो यहाँ से कैलकुलेट कर सकते हैं. Now this was for mechanical oscillator. अगर आप LCR सर्किट के लिए इसकी बात करते हैं damping coefficient की, we said your B is R, M is L, and time period is same. So this would be your expression for logarithmic decrement for an LCR circuit. And this was your expression for a mechanical damped case. And this is for your LCR circuit. So that is one term which is usually associated with your damped oscillations, or to be more specific, with underdamped oscillations. Now coming to the second term that we associate is a quality factor. Let's first talk about the mathematical derivation of this, and then from there we'll try to associate some physical meaning with this also. As the name suggests, quality, it basically roughly you can say that it links with the quality of your oscillation, how much closer you are to undamped case. This basically gives you information about that. Now quality factor is defined as 2 pi multiplied by energy stored in your oscillator divided by energy loss per cycle. Let me write it in words also. This is energy stored in oscillator divided by energy lost in one cycle. Here minus sign has been plugged in because you are talking about the losses here, right? आप energy loss की बात कर रहे हो, so that's why we have plugged in the minus sign here. From here itself, from definition itself, you can say that if your energy lost in one cycle is, let's say, 0, you have an ideal mechanical oscillator or ideal LC circuit. In that case, there is no energy loss. So your energy loss in one cycle is 0. Your quality factor would be infinite in that case. Hence, if you have, let's say, more is the energy loss in one cycle, less will be your quality factor. So quality factor basically gives you an idea how close you are towards an undamped oscillation, whether it's mechanical oscillator or whether it's an LC circuit or electrical oscillator, right? More is the damping, less will be your quality factor. Less is damping, higher will be your quality factor. Now let's get to the mathematical expression for this. We said that energy, we derived it for an ideal mechanical oscillator where we found that energy is directly proportional to amplitude square. And then we said that because we know what is the amplitude in the case of undamped oscillation, so if I want to write my energy, we had e raised to power minus b upon 2mt for amplitude. If you take square of that, you will have minus b upon mt. This would be your expression for energy. Now, talking about the energy loss, if I differentiate it on both sides, dE, E naught is the constant that corresponds to your energy in the circuit if there were no dissipative forces present in here. If you take the differentiation here, you will have minus b upon m is also constant. Your t is the only variable here. So you'll have e raised to power minus b upon m t and then dt. Now, I want to know what is the energy loss in one cycle. Now, for one cycle, your dt is equal to time period, right? एक cycle में आपका change in time is equal to time period, and hence I can say that your dE is equal to minus b upon m e naught e raised to power minus b upon m t multiplied by t. This would be your dE. Plug in the value of E and dE in your expression for the quality factor. You will get 2 pi E is equal to E naught e raised to power minus b upon mt. Your dE is equal to minus this term here. You already have one minus here. So minus minus would become plus here. You will have b upon m. Let's bring t also in the front. And you will have E naught e raised to power minus b upon mt. This will cancel. This 2 will cancel. So you will have 2 pi by t m upon b. 2 pi by t we know is equal to omega. So this is your quality factor. Again, this is your quality factor for a mechanical damped oscillator. अगर आप quality factor for an LCR circuit की बात करते हैं, you will have omega, you will have M, your M was equivalent to L and B was equivalent to R. So this would be your quality factor for an LCR circuit. So these are two terms which we usually associate with your damped oscillations, quality factor and logarithmic decrement. Now, there is another type of oscillations. हाँ जी आयुष बताइए.
मैम एक बार आप क्वालिटी फैक्टर जो ये आपने ऊपर लिखा है क्या एक बार एक्चुअली में एक्सप्लेन कर सकते हैं व्हाट वाज एक्चुअली द क्वालिटी फैक्टर वाज.
What is the physical meaning of quality factor?
यस मैम.
क्वालिटी फैक्टर आपको इंफॉर्मेशन देता है कि आपका जो एक डैम्प्ड ऑसिलेशन है, हाउ क्लोज इट इज टू अनडैम्प्ड ऑसिलेशन. उसका जो डैम्पिंग कोफिशिएंट है उसके बारे में वो इंफॉर्मेशन देता है. बिकॉज यू हैव इन द डिनोमिनेटर एनर्जी लॉस्ट इन वन साइकिल. अगर आपका सिस्टम जो है वो अनडैम्प्ड ऑसिलेटर के क्लोज होगा तो आपकी एनर्जी लॉस जो है एक साइकिल में दे विल बी वेरी स्मॉल एंड योर क्वालिटी फैक्टर वुड बी वेरी लार्ज. Whereas on the other hand, if you have such a system जिसमें आपके dissipative forces ऐसे हैं such that your energy loss in one cycle is very large, in that case your quality factor would be small. So if someone says that you have two systems, for one system your quality factor is 2 and for second system your quality factor is 20, then from there you can say that okay, in this system my dissipative forces are large and in this system my dissipative forces are going to be smaller. So that is the physical interpretation of quality factor.
Okay ma'am. Okay.
Physical meaning that you can associate with it.
Okay ma'am.
So the next kind of oscillations are forced oscillation. And these are the oscillations जिसके हमने starting में video देखा था. And that video was breaking of the glass था या आपका जो bridge collapse हुआ था. They are examples of forced oscillations. Forced oscillations में what you ideally do is that आपका जो ये underdamped oscillation में एम्पलीट्यूड जो रिड्यूस होता चला जाता है. अगेन सॉरी फॉर द पुअर ड्राइंग. यहाँ पे ये जो आपका एम्पलीट्यूड जो है एज अ फंक्शन ऑफ टाइम रिड्यूस होता चला जाता है. जैसे फॉर एग्जांपल यहाँ पे आपका एम्पलीट्यूड इतना लॉस हो गया, यहाँ पे और भी फर्दर लॉस हो गया एंड इस वाले केस में और भी ज्यादा लॉस हो गया. यू अप्लाई अ फोर्स व्हिच बेसिकली कंपनसेट्स फॉर दिस लॉस. आपकी जो मैकेनिकल एनर्जी इंटरनल एनर्जी में कन्वर्ट होके द लॉसेस आर बीइंग टेकन इनटू अकाउंट बाय अप्लाइंग एन एक्सटर्नल फोर्स. और वो एक्सटर्नल फोर्स जो आप अप्लाई करेंगे दैट वुड बी इक्वल टू द अमाउंट व्हिच कुड कंपनसेट फॉर दिस डिक्रीज इन एम्पलीट्यूड, सो दैट आपका जो एम्पलीट्यूड फिर फाइनल आए वो आपका एक आइडियल जो एसएचएम में आपका एम्पलीट्यूड आता है वैसा आपका एम्पलीट्यूड आना स्टार्ट कर दे. That's your forced oscillation. I think my time is up, so we'll start from here in the next class. Anyone has a quick doubt, we can take that.
Ma'am, can you just take to the logarithmic decrement slide?
Logarithmic decrement slide. हाँ जी बच्चे.
Just I want to write something from here.
Okay, that's fine. So, but anything that I'm writing here, it's also given in the PPT also. But nonetheless, you should still try to write with me so that, you know, because in PPT, everything appears suddenly and then it gets confusing.
Okay, okay. I have written, ma'am.
And When you are done, please do let me know.
Ma'am, I have done.
Okay. So I need to sign out now. So see you tomorrow then.